Okay, Algebra 2, let's see if we can apply what we've learned about graphing sinusoidal functions and if we can apply it to the real world. So, we're going to go through a few different examples that will offer you guys the opportunity to solve real-world problems, to experience ways in which modeling data with sinusoidal functions is valuable. Each of the three examples we're going to do supports why we would look at sine and cosine functions to model real-world data and why we may not use them. So here's a little bit of reading we're going to do in the beginning. Also, we will be doing some graphing, Scatterplot graphing, which you should have done in Algebra 1 as a first test. I graphed one by hand. You should have learned how to do scatter plots in your graphing calculator, but you can also use Desmos. I'm going to show you what I did by hand, and then we'll go ahead through Desmos and do it again. So let's look at our opening exercise. I need you to read this. I'm going to read it out loud, and then if you might want to push pause and read it again on your own. So anyone who works on or around the ocean needs to have information about the changing tides to conduct their business safely and effectively. People who go to the beach or out onto the ocean for recreational purposes also need information about tides when planning their trip. The table below shows tide data for Montauk, New York, from May 21st and 22nd, 2014. The heights reported in the table are relative to the mean lower low water. Okay, that's an abbreviation they're going to use now, mean lower low water. The MLLW is the average height of the lowest tide recorded at a tide station each day during the recording period. This reference point is used by the National Oceanic and Atmospheric Administration, NOAA, for the purposes of reporting tidal data throughout the United States. Each different tide station throughout the United States has its own MLLW. High and low tide levels are reported relative to this number. Since it's average, some low tide values can be negative. NOAA resets the MLLW values approximately every 20 years. Okay, so here is the Montauk, New York tide chart. The first question you see in your classwork is part A. It says create a scatter plot of the data with the horizontal axis representing the time since midnight on May 21st and the vertical axis representing the height in feet relative to the MLLW. I need to point out that the x-axis is supposed to be the time since midnight on 5/21. So if we see here 2:47 a.m., 9:46 a.m., 3:31 p.m., that needs to be changed to the 24-hour time. 10:20 p.m. needs to be changed also. And then here, this has to be the time since midnight on Wednesday. So our time is going to keep on going chronologically. We're not going to start out for a new day and go back to 0 for midnight on Thursday. And I'll show you what I did, but I want to talk through just your thought process and what you need to be thinking for graphing your scatter plots. So what I did is I changed every one of these times. For instance, 2:47, the minute 47 has to be part of 60, which gives us 2.78 hours after midnight. Okay, that's for this first one. For instance, this one, 10:20, I need to first figure out 20 over 60, which is 0.33, so 10.33 hours. But we need to add that to the previous, well, we need to add that, it's the 24-hour time, sorry, we don't add that one because we're still on Wednesday. So our actual time would be 22.33 because we're after noon. So remember the 24-hour time goes 0 to 12, then it keeps on going to 24. It doesn't start over AM, PM. And then, for instance, let's do this one. We have 35 over 60, which gives us 4 points. Let's see, where did I do it? 4.58, which is actually, we're in the afternoon of Thursday, 16.58 plus the previous day, which is going to be 40.58. So we need to do Thursday. So we add a whole 24 hours plus the 16.58 hours of the current day. Well, let's look at my chart. So you see here all the times on the table in your classwork. I changed to decimals, so the minutes have to be part of an hour. And then I made sure I kept going sequentially. So when we switched to Thursday, I had to add 24 to each time to make sure I kept going sequentially. So for my scatter plot, my x-axis should be from 0 to 48. Hours. I would do a scale of 1. And then my y-axis, my height actually goes from negative 0.02 feet all the way to 2.51 feet. So I have my x and my y-axis. As you can see here, I plotted all the dots for my scatter plot. I did not have graph paper, and I really, really hate graphing without graph paper. But I was at home this weekend. I didn't have any graph paper at home, and I usually do. I think my kids stole it. So I did my best with regular paper and putting a scale on here. If you look, I drew my x-axis. I went from 0 to 48. Then I sort of cut it in half for 24, cut it in half for 12, and 36. No, yes, that doesn't look like half. And then I just did 3 tick marks in between. So it looks pretty good. Pretty happy with how things worked. My smallest y value, this would be negative 0.4, is 0.02. So that's pretty close to the x-axis. So I did, you have the chart in front of you. I took every value at 3 hours. Well, it's actually 2.47. Actually, it's 2.48 because it's 2 hours and 47 minutes, which when you change that into a decimal, it should be 2.48. I graphed all of my points. So 2:47 a.m., 9:46 a.m., 3:31 p.m., etc. So I graphed everything using the decimals that I calculated and graphed all my points. Okay, so that was question A. Question B, oh, actually no, pause. I'm going to go ahead and graph this on Desmos. Okay, here you'll see what I've done in Desmos. You can create a table by just hitting this button. It's a drop down, and you can select table, plug in your x and y values, and we've got a scatter plot here. It's pretty awesome. Part B of the question, what type of function would best model this set of data? Explain your choice. You know, we don't really have a set maximum here or a set minimum, but we're pretty close. You can see that we've sort of got, if I just connect the dots, a sine or a cosine function, which is pretty fun. The book would say we have a sinusoidal function, and that would best model the data because we've repeated a high and a low and a high and a low and a high and a low over fairly regular intervals of time, and we've got about every 6 hours. So regular here, about every 6 hours we change, and we go from high to low to high to low, a decently regular minimum and maximum for everything. Let me go ahead and erase all this so that we can look at a clean graph. And amazingly enough, we're going to come up with an equation to this great graph here in a little bit. So graph paper would be your best option. Desmos would be awesome. You could do this in your graphing calculator using the Scatterplot. Or paper, which I did a decent job of. All right. Here's the graph paper they gave you in the book. Notice they went from 0 to 50, which is pretty close, -2 up to 2.8, which we only need about 2.5, but you can use this to graph it too. I actually didn't even have this at home, so we did that. All right, example 1, write a sinusoidal function to model a set of data. On the scatter plot you created in the opening exercise, sketch the graph of a sinusoidal function that can be used to model the data. Hold on. So, got a new slide. On the scatter plot you created an opening exercise, sketch the graph of a sinusoidal function that could be used to model the data. I opened up my scatter plot in Desmos and I drew in the sine function. Now I've already done the work to get the equation for the sine function, so that's how I drew a sinusoidal function over it. But if you did your scatter plot by hand, you would just, connect and try to make everything in a cycle that's even. I didn't copy the x-axis down, sorry. But we saw that this repeats about every 6 hours, so you can pretty well, nicely sketch a sine or a cosine function that goes through a maximum and minimum all the way to the end, right? So now we're going to go through the pieces and the parts of the midline, amplitude, etc. So what are the midline, amplitude, and period of the graph? You have the graph in front of you if you've sketched it, or you can go back and look at the previous slide. The midline is going to be sort of the maximum plus the minimum divided by 2, which also gives us our amplitude. And we had a definition for that a few lessons ago when we first learned about it. So if we do negative 0.02 plus 2.51 divide by 2, we get 1.246 something, so that rounds to 1.25. That means our amplitude is 1.25, and our midline is y equals 1.25, right? And if you look at the graph, our period, if I could spell, is about 12. Okay, so just try to trace through where you think it starts, all the way back to the beginning, and that's approximately 12. Cool? Here's where things get a little sticky in my mind. Estimate the horizontal distance between a point on the graph that crosses the midline and the vertical axis. So we're looking for about the distance where everything shifts just a little bit. Let me copy the graph back in here so I can point it out. Okay, if I draw the midline in, that's y equals 1.25. It's hard to draw a perfectly awesome line. And if you look right here, okay, that's our shift. So this is actually a sine function, but we're shifting just a little bit. I'm saying we're going to shift about 0.5, right? So at the end of this would be our x minus h plus k. This would be our plus k. Nope, our plus h. Minus h. Minus h. So our horizontal shift is positive 0.5. In the curriculum, they say it's positive. Let me erase that. That'd be confusing. In our curriculum, they say it's 12.5. So they're actually going to start their graph right here and get it going from the sine function. And that's fine. I mean, that's like a period, so we're just moving it over one more and starting 12.5. I mean, goodness, you could start at 24.5. That's fine. That's just where they chose to start from, but I thought it might be good to show you how it starts just a little bit off from horizontal. You're shifting to the right just a tad bit. So that's the answer to part C. Either about 12.5 hours or 0.5 hours. either one would be acceptable. Sorry, this would be a horizontal shift is about 12.5 hours or 0.5 hours. So write a function in the form a sine omega x minus h plus k to model this data, where x is the hours since midnight on May 21st, and height in feet relative to the MLLW. So we said amplitude was 1.25, your midline was y equals 1.25, the period was 12, and that's really all we need. Remember, we can figure out omega is 2 pi over your period. So from this information, we can write our equation. We have the amplitude, omega. You can simplify that if you want. X minus h. I'm going to stick with 12.5 plus k. Pretty fun. We just made an equation from a graph. Yay! So next, exercise 1. The graph of the tides at Montauk for the weeks of May 21 through the 28th is shown. How accurately does your model predict the time and height of the high tide on May 28th? That'd be up there. The maximum value that we talked about before was 2.5. Okay, that's because our amplitude was 1.25 from the midline, so that's our maximum. So this right here should be our maximum that we calculated from the previous stuff. Sorry about that. So we're a little above maximum, okay? We're at almost 3 feet. So we're off by about 6 inches, which is actually a lot. So are tides an example of periodic phenomena? Why do you guys think this is true? So to some degree, tides are an example of periodic phenomena, but they're not a perfect model. Tides are influenced by the moon. The moon orbits the Earth at a regular interval of time, but the moon is different distances away from the Earth at different parts of the month. So the influence of the moon on tidal heights would be periodic up to a point, since there's ongoing variation in heights due to a wide variety of natural factors, not just how far the moon is away from the Earth, but there's more things that have to do with the location of the moon versus the oceans than I even understand. The moon is an elliptical motion around the Earth, which is one way that it gets influenced, but it's to some degree, yes. What are the limitations of using a sinusoidal function to model the height of tides over a long period of time? At different times of the year, the height of a tide varies widely, so not all tides are perfectly symmetric. So there are limitations. All right, let's get into the digital sampling of sound. Here things got a little more confusing for me, but we figured it out and we're ready to go. So let's see if I can help you figure it out. Let's start by reading this. When sound is recorded or transmitted electronically, the continuous waveform is sampled to convert it to a discrete digital sequence. If the sampling rate, represented by the horizontal scaling, or the resolution, represented by the vertical scaling, increases, the sound quality of the recording or transmission improves. Okay, stop there for a second. When someone hears a musical note, his or her eardrums are sensing pressure waves that are modeled by sinusoids, or a combination of sinusoids. That's our periodic motion. As the amplitude of the wave increases, the note sounds louder. So as the amplitude increases, the note is louder. As the frequency of the wave increases, which means the period is increasing, which means the period is decreasing because they're inverse. Let's change that. The pitch of the note increases. A pure tone of the note A has a frequency of 440 hertz. So A, frequency equals 440 hertz, which means the graph of the sinusoidal function that represents the pure tone would complete 440 cycles in 1 second. Yikes. This function would have a period of 2 pi over 440. If the sampling rate increases, the sound quality improves. Cool? So if you look at the rest of the problem, the data graph below represents 2 different samples of pure tone. One is sampled 8 times per unit of time at a 2-bit resolution, and the other is sampled 16 times per unit of time at a 4-bit resolution. Okay, and you'll see that by our graphs. So here we took 8 samples. We're still at 16, but 2, 4, 6, 8. So we only took 8 points. 1, 2, 3, 4, 5, 6, 7, 8. There's a repeat because we start and we stop. And here's 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Again, between there and there, there's a repeat. So first question, which sample points would produce a better model of the actual sound waves? Explain your reasoning. So you're actually going to get a better model with figure 2 because you sampled it 16 times, which gave us a better sinusoidal function. The curve fits very accurately with the 16-point sampling. The 8-point sampling, not as much. We've got a point out here hanging out. Over there, we've got 2 that are right on the 0 axis, which isn't very accurate. So graph 2 does. Okay. Okay, find an equation for a function g that models the pure tone sampled in figure 1. So we're going to have to come up with a few of our data points. We can figure out our amplitude, our period, and our phase shift, our H, and then the midline, right? So just looking at the graph, we're trying to figure out all these values. First of all, let's look at period. We are at 16. So our period is 16, which means omega is 2 pi over 16, which works great. This gives me a decimal of 0.39. Our phase shift, first we need our midline. It's hard to figure out the midline if you just try to figure out sort of the average of all these points. I mean, we look to be about 8, a little above 8. Quite a few times I've just calculated. I mean, if this is, we're only looking at 8 points. I mean, if I look at 1, 2, 3, 4, 5, 6, 7, 8 and average them, I get 9. If I skip that one and look at all of these, my average goes up and down. So we're just going to say that we have a midline of about 8. Okay, the book's midline is 8.6. There's no reason for me to be able to figure out that it's a little above 8 or a little below 8. So we are at a midline of y equals 8. So our amplitude has to go maximum and minimum. We're just going to say we have an amplitude of 8 because that's our maximum and our minimum. Now, we know our period is 16, but we have a phase shift. So if this is a sine function, I need to figure out where I start. That was a bad line. So straight down, we're at about 1 point something. I don't know, 1.7, 1.5. We can keep it easy and do 1.5. So that would be our phase shift. And we go from there, which means our period isn't exactly 16. Looks like we have a period of beginning to end 2, 4, 6, 8, 10, 12, 12.5. So omega is, I don't know why I did that, is 2 pi over 12.5 is 0.5. So we're going to use that one. Cool. So our h was about 1.5. Okay, let's write our equation. G of x equals our amplitude, sine omega, which is 2 pi over 12.5, or 0.5, x minus our phase shift, 1.5, plus our vertical movement, which is 8. Cool. Okay, let's do it again. Okay, let's try to come up with our equation for this one. I need amplitude, period, midline, h. Okay, midline is really what we have to come up with first. So I averaged all these points together, skipping this one, and then I averaged all these points together, skipping that one, and I got 7.7 and 8.4. So let's just pick this one at 8. And again, when you're working these problems by yourself, hopefully it's a little more apparent. If not, you can just write me a little note, like, hey, I picked 8, and this is why. So my midline is y equals 8. Amplitude, I'm going to go max and a min, 8 up, 8 down. Period, hold on, let's look at it. And h, we need to look at that too. So let me fix this midline just a little bit. See if I can make it a little more on the line. Not really. Okay, let's see how far we're shifting. About right there, so 4, 3, 2. It's, 1 point something again. So 1 point, let's say 5. So fine, it starts there, it stops here. So we're at 13, 14, so that's 14 minus 1.5 through 12.5 again. So omega is 2 pi over 12.5, which we did the math a little bit ago, and we got 0.5 as that. So we can write our equation. H of x equals amplitude, sine, our omega is 0.5, x minus 1.5 plus 8. Now, really quick, in the book, they're always giving us our equations like this, which used to throw me off. Now I'm good. They multiply that omega through. Oh, hold on. Let's get that right. 0.5x minus 3 plus 8. And I used to get really confused, but I know just to take that, to factor this value out to get that equation back, because this equation is the standard equation that we've been learning from. So I'm trying to get us back to that standard equation. And in my book, the standard equation that they have come up with is actually what we have. Using the raw data, they were able to, I think, sine fit 8.6436 sine of 0.5 x minus 1.7 plus 8.3651. There's no way for us to come up with those big numbers. I mean, we're just trying to read a graph, right? 7.8464, that's what they had for their amplitude. The omega 0.49 x minus 1.47 plus 7.8760. So we did the best we could with ours. I mean, we're trying to read a graph that's drawn for us. So we did really good. And then this right here is the standard, the actual sinusoidal function for the models that were given, because they were notes. Let's see, pure tone. They're a pure tone, so there's going to be an equation that matches a pure tone, which is given right there. Okay, now let's move on. Stock prices have historically increased over time, but they also vary in a cyclical fashion. Create a scatter plot of the data for the monthly stock price for a 15-month period since January 1st. Okay, let's do that together. Okay, we're going to see this graph again in a minute, but I just took a picture of my textbook to give you a scatter plot. Okay, we're going to use a scatter plot as we go through the lesson. I guess I can make it bigger. So we have an, excuse me, a y-axis that maxes out at about 22, and our x-axis goes from 0 to 14. Our minimum y, I mean, just looking at the data, the smallest one I can see is 18.25. So if we look right here, that's that one. So that's all that we really need as far as our scatter plot goes. But question 2 says, would a sinusoidal function be an appropriate model for this data? Explain your reasoning. I would say no. Not an appropriate model because the data are trending upward as time passes. That maximum on the graph just keeps getting higher and higher and higher, and that minimum keeps getting higher and higher and higher. And a sinusoidal function needs to stay pretty much the same maximum and the same minimum. It shouldn't increase over it very often. We can model the slight upward trend in this data with a linear function. Okay, if we add a sinusoidal function to the linear function, we can model the data with an algebraic function that displays an upward trend but also varies in a cyclical fashion. Wow, didn't know we could do that. But let's work through it. Find a sinusoidal function g that when added to a linear function f will model this data. Trying to find the period here. Looks like I've already written on my paper copy. I mean, if we start there, we have 1, 2, 3, 4, 5.5. So omega would be 2 pi over 5.5. And that works. Our amplitude, yeesh. If I try to draw a line through this mess, we have to be a plus and a minus, so that looks to be about 20.5, and that looks to be about 21, wait, this is 21. So that's our midline, is what I'm saying. Looks like my maximum is half a one, a little more than 1. Let's just say a little more than 1. Our phase shift, yeah, that one's got me confused. I started it right at where we would cross the axis. So if we look right here, like that's where I drew my period starting right there. But it looks like my midline I'm making a little bit higher. So I'd say this distance right here would be my phase shift. And those go in 2s, so about 0.5. And I actually think that would be more of a, well, let's keep it at that. And then the midline. Goodness, y equals, I don't know, 20.5. Okay, basically on this one, students' answers will vary. So let's try to write an equation. G of x equals my amplitude, sine my omega. We're going to keep it at 2 pi over 5.5. X minus, I think about 0.5, plus 20.5. Okay, that's messy. All right, I'm going to get a new sheet here and show you something else. The equation that they came up with, which is the one we're going to use now, we worked through the heartache of trying to come up with our own equation, and we did really well. The part that we're going to go with theirs, they have x minus 4, so a phase shift of 4, and they don't have any midline, any vertical shift. Okay, no big deal. So write this down. Oh, I need another parenthesis. And that's what we're going to use for part, for the next part. So I just need to hold on to it. Okay, so let's look at something else. Okay, we already did, so let's look at 4. Let S be the stock price function as the sum of the linear function listed above and the sinusoidal function in exercise 3. So what we have here, that's where we're going to raise it by, they have 19.5 plus 13x. This right here is the linear function. And then they're going to add the sinusoidal function. 1.1 sine, everything they have, 2 pi over, you know what, let's rewrite this. So S of x equals our y-intercept plus our slope plus our sinusoidal function. I am assuming that this right here accounts for, we would have had plus k, that accounts for it. The other thing I want to show you, and I'm going to take a picture of it in a second, is I put all this information into a scatter plot in my calculator. And you can do a linear regression, and you'll get the 19.5 plus 0.13x. Okay, and then you can actually do a sine regression. Make sure that's the wording it uses. You go stat calc. Yep. Sine reg, and it was really awesome. I got 0.95 sine 1.03x. You know what? I'm going to give you this one in just a second. But yeah, I put a sine reg in there too and got an equation. So that was really cool, but that's okay. I'm going to add the graph of this function to the scatter plot. How well does it appear to fit the data? So hold on a second. Lots of stuff going on this page, but don't worry about it. worry about it because we're going to learn about it, but don't stress about it. Here, right here is the graph that I've shown you a few times, the answer key from my textbook. We see the dots are the scatter plots. And then they did their sine equation. So this is their equation for a line plus the sine equation all added together, because you see it sort of increases. But we were trying to figure out how to do that, and I wanted to show you. So the first thing I did is went into Stat Edit, and we have list 1 and list 2, and I typed in the table from the classwork. Okay, then I went to Stat. Actually, what you see here is just the graph. So you can do stat plot. Make sure plot 1 is on. You can do zoom stat to get your right window, and this is what will pop up. These are just the scatter plot. So it's all of the data, you know, the x and the y plotted together. Then I did a linear regression and got this equation for a line right here. And amazingly enough, it's the same equation that the textbook came up with. I think they had 19.5 here, but I had 19.4, and that's close enough for me. And then I went ahead and plotted it within my scatter plot. Then I did a sine reg, so a sine regression, and got this equation right here. Pretty darn close. I think the book came up with 1.1 there. And let's see what 2 pi over 5.5, 2 pi divided by 5.5, 1.14. I got 1.03. It's all right. So this equation right here, my sine reg. And you'll see it's just a sine function, okay, very horizontal, doesn't increase at all. It's not like this one, which goes up. But the last thing that we were going over in this example is how, if you add the linear regression with the sine function, if you add those two together, your sine function will increase over time. Watch this. So here we have the linear function and the sine function added together. So our equation looks something like this. Y equals mx plus b plus 0.945. I used mine. See, I typed it into my calculator like this. Sine of 1.03x plus 2.56. In the equation I gave you earlier, I factored out the 1.03 to show omega by itself. Close parentheses, that's right. And the equation originally says plus 20.33, but if we have the y-intercept there and the vertical translation there, it's double, it's too much. So we're translating it vertically 19.4 and 20.33. So I just took one out. We're just going to account for one of them because they're pretty close. So I typed that into my into my y equals in my calculator, and got the increasing sine function, which I thought was totally cool. Pretty awesome. So I hope you learned something new during this exercise. I would love to show you again, if not, because I thought that was so fun. But let's move on. Let's talk about the stock market. Okay, this last thing, we have a graph of the same stock through December of 2009. Will your model do a good job of predicting stock values past the year 2005? That's a mess. I can't imagine it doing a good job. We've got a sharp rise here, a sharp fall here. You know, it looks like we're sort of going up and down, even increasing there, but then awfulness happens. So no, not a very good job at all. Okay, we have a sharp rise. And then a plummet. It's a technical term. And then another sharp rise. So not a good job. So what event occurred in 2008 to account for the sharp decline in the value of the stocks? This would be the financial crisis. Most adults are aware this happened. You guys may not so much. So the financial crisis occurred. Crisis, can't spell. The financial crisis occurred, and that was sort of the start of our little recession that we had in the U.S. Okay, housing was a big part of that. What are the limitations of using any function to make predictions regarding the value of a stock at some point in the future? Lots of variables. People that play the stock market or people that work with the stock market, they are aware of so many variables that can happen, and predicting the future is near impossible. The Shellhammer family, we have somebody play with the stock market for us because I don't have time to look at all the variables that could possibly happen, and all of the unforeseen circumstances that could take place. So we don't do it. Someone else does it for us. Okay, lesson summary. Periodic data, we've been talking about it. They've been calling it sinusoidal data as far as waves go. Sine or cosine functions may not perfectly fit most data sets, but that's where we learn to use multiple functions to model a data set, linear and sinusoidal. Let's see, if possible, plot the data together with a function that appears to fit the graph. If it's not a good fit, adjust it and try again. The sort of summary, play around, get a feel for what's going on, and you'll get better at it as you practice. Phew, good work today. That was a long one.